So this will be the third lecture from chapter 6. So in this lecture we cover this concept of Hess's law. So Hess's law, so how do you determine the heat of a reaction if you can't study the reaction in a calorimeter? So you can use Hess's law. So basically this is just a method to determine the delta H for a reaction. Okay, so let's take a couple of examples. So if you want to know delta H for the reaction in A, so 2 moles of graphite plus 1 mole of O2 gas to make 2 moles of carbon monoxide gas. So what is delta H for this reaction? So the problem is that this is a difficult reaction to study in a calorimeter. Since the reaction doesn't want to stop at carbon monoxide, the reaction would continue to make some carbon dioxide as well, and so that complicates it. So what you can study, however, is the two reactions below, B and C. So if you take a mole of graphite and a mole of O2 and combust them to make a mole of CO2, so delta H for that reaction is known. It's negative 393.5 kilojoules. And if you take 2 moles, so reaction C is known. If you take 2 moles of carbon monoxide and a mole of O2 gas, you can make 2 moles of carbon dioxide. So delta H for that reaction is known. It's negative 566 kilojoules. Okay, so what you do with Hess's law, we're going to use combinations of B and C, and we're going to manipulate those equations of these known reactions with known delta H to determine delta H for the reaction of interest, which is reaction A, which we don't know what delta H is. Okay, so what we want to do is we want to compare reaction B to the reaction of interest A. And then we want to compare reaction C to the reaction of interest A. So let's compare reaction B to A, and what we want to do is we want to look for a chemical in A and look for a chemical that is in A and B, but is not in C. Okay, so if we compare A and B and look for a chemical that's not in C, so we wouldn't want to use O2 because O2 is in B and C. We wouldn't want to use, let's see, carbon dioxide because carbon dioxide is in B and C. But if we look at graphite, so graphite, however, is unique to A and B. So it's not in C. And then we want to do the same for compare reaction C to A. And we want to look for something in C that is also in A, but is not in B. So we want to find something that's unique to A and C, just like we found something unique to A and B. So if we compare A to C, so again, we don't want to look at O2 and CO2 because they're both, they're in both B and C. But carbon monoxide, however, is in C, but it is not in B, but it is in A. So what's unique here is carbon graphite, and what's unique, and when we compare C and A, is carbon monoxide. Okay, so now we want to manipulate equations B and C to make those unique chemicals, so to make the chemical that's unique in B to look like what it is in A. So graphite, so in A there's 2 moles of graphite, but in B there's only 1 mole of graphite. So what we need to do for B is we need to multiply everything times 2, so that there would be 2 moles of graphite. And then, so in B right now there's only 1 mole of O2 and 1 mole of CO2, but we're going to multiply it all by 2. So now there will be 2 moles of O2 and 2 moles of CO2. And so whatever you do to the stoichiometry, you also have to do to delta H. So if we multiplied all of the chemicals, the moles by 2, then we have to multiply delta H by 2 as well. Okay, so then now let's compare C and A. So we said what is unique is carbon monoxide. Well, in A, carbon monoxide is on the right of the arrow, but in C, it's on the left of the arrow. So we need to make C look like A. So we need to make carbon monoxide look like A. So what we need to do to C then is we need to reverse it. So we need to reverse the direction. So basically that means take whatever's on the left, the right of the arrow and move it to the left, and take whatever's on the left of the arrow and move it to the right. So I haven't done that yet, so we need to reverse this. So we're going to take this and we're going to move it over here, and we're going to take these and we're going to move them over here. Let's get rid of this. Whoa, whoa, whoa. Let's move this over here. And put this right there. So now we've changed the direction. Now C is running backwards. 2CO2 is making 2CO plus O2. So it doesn't mean that reaction will be easy to do. We're just doing, basically, we're doing math here. We're manipulating the equation. So what happens if you, what do you do if you reverse the direction of a reaction? You just change the sign. So now this would be plus 566 kilojoules. Okay, so now what we can do is we can add these two reactions together. So we can add, so this would be the new B, and this would be the new C, after we've manipulated those equations. So we're going to add those new B and new C together, and if we add them together, then we also add the delta H's together. So how do you add chemical reactions together? Well, anything on the left of the arrow in one reaction can cancel something similar to it, or something that's the same to it, on the right side of the arrow in the other reaction. So there's two graphite here in B, but there's no graphite in C. So the graphite stays. Nothing happens to the graphite. There's two O2s here on the left of this arrow, and on the right of this arrow in the B, there's one O2. So one of those can cancel. This can be canceled, and then there would be one of these left. So that's where we get this O2 from. So anything on the right of the arrow that's not canceled out between B and C will stay in the new reaction. And then for CO2, let's see. So we have two CO2s on the right of this arrow, and we have two CO2s on the left of that arrow. So those two are on opposite sides of the arrow, so they cancel each other out. So the CO2s cancel out. And then what's left is we have two CO here in B and the new C, but there's no CO in B, so there's nothing to cancel it, so it will be in the new reaction. So now we have two graphites plus one O2 to make 2CO, and that is the original equation A that we were interested in. So now all that we have to do is add the delta H's together. So we'll take this times 2, so that gives you negative 787. And we change the sign of this since we reversed the direction of the reaction. So positive 566, so we add those two together. So this reaction's delta H would be negative 221.0 kilojoules. So this reaction is determined to be then exothermic. How do we know it's exothermic? Because it is negative. So it's exothermic by 221 kilojoules for every 2 moles of graphite that reacts with 1 mole of oxygen gas to make 2 moles of carbon monoxide. So even though we can't study this reaction experimentally very easily, if at all, we can calculate what its delta H would be. Okay, so let's take another example. So let's say we want to know delta H for this reaction. Maybe we could study it in a calorimeter, but of course that requires a lot of time, a lot of effort, and you have to have some money because you have to buy the chemicals and the equipment, right? So it would be better if we could just use something like Hess's law and calculate this and not even have to do the reaction, not even have to do the experiment. So that will work if there are reactions that are known that you could take combinations of those reactions to get the reaction A that we're interested in this case. So if you were given reactions B, C, and D, how can we manipulate those equations and then add them together to get A, right? That's the goal. So to do that, then we want to compare B to A and find something that is unique that is not in C and D. And then we want to do the same with C, compare C to A and find a chemical that is unique that is not in B and D. And then we want to do the same with D, compare D to A and look for a chemical that is unique to A and D that is not in B and C. Okay, so if we compare B and A, so what is unique to those two reactions that is not in C and D? So let's see, so is it H2? No, H2 is in B and C, so H2 is not unique. Is it N2? No, N2 is in B and D, so N2 is not unique, but what is unique is NH3. Right, NH3 is in A and B, but it is not in C and D. So now we know how to manipulate B to make NH3 look like it does in A. So it's on the right of the arrow in B, but it's on the left of the arrow in A. So one thing we have to do is reverse B. So that means we need to change the sign of delta H. But also we have two NH3s here, but only one there. So we need to cut B in half, which means we need to divide delta H by 2. So we're going to take B and we're going to flip it. So we're going to reverse B and cut in half. Right, so NH3 is going to go to the left of the arrow, N2 and H2 is going to go to the right of the arrow, and then we're going to divide everything by 2. So now there's only one NH3, so now there's 1/2. Since there's one here, now there's 1/2, and there's 3 H2s originally, so now there's going to be 3 halves. And delta H is going to be positive, and it's going to be cut in half, right? Okay, so what's unique here is NH3. So now if we compare C and A. So we already established that H2 is not unique because it's in B and C. Let's see, how about CH4? Is it unique? Well, how about graphite? Is graphite unique? No, because graphite is in both C and D. So what is unique here is CH4. Let's undo that. Let's make this a different color. So CH4 and CH4 is only in C and A. So CH4 is unique. So what do we need to do to C to make CH4 look like the CH4 in A? Well, it's on the right of the arrow in C, but it's on the left of the arrow in A. There's only one in both cases, so we don't have to change the stoichiometry any. We just have to reverse the direction. All right, so there we reversed. Here we reversed and cut in half. Okay, so C, all we got to do is reverse it. So move the CH4 to the left, move the C graphite and the 2H2 to the right. And so we're going to have to change the sign of delta H to a positive 74.9, right? So we move the CH4 to the left, graphite and H2 to the right, and change the sign. Okay, so now we got to do the same thing to D. So what is unique in D and A that is not in B and C? And the answer is, let's see. So it's not N2 because N2 is in both B and D. It's not H2 because H2 is in both C and B and D. It's not graphite because graphite is in C and D. But HCN is in D. It's not in B and it's not in C. But it is in A. So HCN is what's unique. So we need to make the HCN in D look exactly like it does in A. So there's one of them in both, and they're both on the right side of the arrow, so they already look the same. That means we don't have to do anything to D. So D we keep the same. Right, so same D. Okay, so that's our three new equations, chemical equations, and now we need to add them together. So let's see, so let's start adding things. So we have a half N2 here and a half N2 there, so they're going to cancel each other out. We have a graphite on the right of the arrow here and a graphite on the left there. So they're going to cancel each other out, right? One's on the right of an arrow and one's on the left of the arrow, so they're on opposite sides of the arrow, so they cancel. NH3, there is no NH3 in C or D, so it's going to remain. So that will be part of the new equation. CH4, there's no CH4 in B or D, so we can't cancel CH4 out. So it's going to remain. Let's see, how about H2? So there's 3 halves H2 on the right. In B, there's 2, so that would be 4 halves, right? On the right in C, and there's 1 half on the left in D. So we have 7 halves minus 1 half, so that would be 3. H2 gas, right? 7 halves minus 1 half, so 6 halves, so that would be 3 H2s. And then HCN, there's nothing, HCN is only in D, there's no in HCN in B or C to cancel it, so the HCN remains. So if we add those three equations together, that's the equation we get out, which is the equation that we are interested in to begin with, an A, right? So now we just had to add these three values of delta H together. So positive 45.9 plus positive 74.9 plus positive 135.1 gives us an answer of the delta H for this reaction is 255.9 kilojoules, right? So we wouldn't have to go in lab and measure this. We can just use Hess's law, manipulating these three equations and adding them together to get the value of delta H. So we know that this reaction would be endothermic by 255.9 kilojoules. And that's how you use Hess's law.